This video will go into some of the more particulars of the MATLAB code for this lab and how you want to use it to set things up and what you would need to do with this lab to actually complete the assignment. So with this lab, all of the code for running the models is given to you. There's the SIR model code, look over here on the side, SIRQ, SIRQV. These are the three different models that you're going to be running over the course of this lab. And the main things you are going to be doing for the assignment is looking at the results and changing parameters. So this method, we pull it up real quick for SIR model. The first two values of the two parameters, R and C, these were alpha and beta in the last video, and initial conditions for that point, as well as the final time. Final time is mostly going to be set for you, but you're going to be changing these different parameters here. So in this first method call here, I'm calling SIR equal to this method of an R value of 0.1, a C value of 0.01, initial condition of 0.99, 0.1, and 0, and this final time that is set up here at 800. So if I want to change parameters, I can just change these values. Say I make this 0.2 and this 0.005. I can run this section again, and the graph will change. And you can see how changing these parameters affects the graph and the results. And if you look at the code here, S is given in blue, that starts here and drops off. I, the infection population, is given in red, spikes up and then drops. And R, the recovered or removed population, is given in black up here. So most of the ideas of this lab will be adjusting parameters to get certain results out of the lab. The SIR model is pretty simple, it doesn't do too much with it, and you only get this one plot here. But for the later models, there's more complications involved, and so more things that can be adjusted to make certain changes. So for instance, here we have the SIRQ model with a set of parameters, and now, as expected, there are 6 parameters before the initial condition, which is set up here, and the final time is in there as well. And we run this. And the big thing to notice here is there is what's called a subplot command here. We can see what that does if we actually pull this outside of MATLAB. So let me run this section to grab the information. And let's see what this looks like in a normal MATLAB plot type interface. Copy all of this code, paste it here, and hit enter. This is what pops up. And so the main point of subplot is it lets you put multiple plots in the same figure, and it lines up the axes for you, right? So if you notice here, the x-axis is all completely aligned correctly. So it allows you to sort of see over time how all these things behave instead of just a few of them. And you can do this with anything you want, but it works nicely for this because now you can see I can see S, I, Q, D, and R all at the same time and not have them all separately or have them all in the same graph, which would be a little bit confusing because stuff is overlapping. But seeing them in 2 plots here makes it a little easier to understand what's going on with this setup. Now, for some of these parts where you're adjusting parameters, there's different sort of things that you're aiming for, right? So for this section, you're actually aiming for looking, when can I make I plus Q below a certain maximum value? So the graph you're given is I plus Q. What you're going to want to do is take the appropriate parameter here and adjust it. Say we bump this up to 0.02. That got a little bit lower, but not a lot lower. So if I want to get it even lower, I can keep adjusting it to see what happens. And you're going to want to figure out for this lab, based on the situation given in the problem, what parameter are you adjusting or parameters are you adjusting? And then play with it to get the desired result that you want. So for instance, maybe if I make this like 0.5 and run that, now that's really low. Now that's good. Maybe that's too low, and I can bring that back a little bit. And you'll want to just keep playing with these parameters, keep adjusting them and messing with them to get to the threshold that you're looking for. You don't have to get too exact to it, but play with it a little bit, mess around, and see how you can see where this is going to get adjusted to over time. And then further down, you're going to be doing similar adjustments now, focusing on D, which is sort of the deceased population, and trying to get that into a certain area as well. And similar things for vaccination. And so the goal is to really see how different physical conditions impose different constraints on the differential equation system, and then how that system gives rise to solutions that make sense based on these constraint adjustments. Right? If we want to, for instance, assume that people start off being immune to the disease, we can put a value in for the initial condition for the R value, right? There can be a set of recovered people that just start that way. And we can see how adjusting that value affects everything else, as like it should. More initially immune people means the disease spreads less because there's less people for it to infect. And so you can see how all of these different physical changes adjust parameters in the differential equation, which then result in a solution that matches that physical adjustment. And so that's the main point of this lab, is to get you to see how all those things relate and see how it comes out of the code here as well. You don't have to worry about the actual numerics of running this method. It does all that for you. What you're doing here is adjusting parameters, moving things around, and trying to get certain things under thresholds to see what conditions have to arise for certain solutions or certain things to arise from a disease modeling spread equation to achieve certain outcomes. As context, this lab was written, designed, and formulated and put together mostly during the COVID-19 pandemic, and so it's very much issues on the front of my mind and everyone's mind right now. And this idea of how can we adjust certain things in society that should result in a change in how the disease spreads, and what does that give us in terms of a solution, how it looks, is a really important skill to have as an engineer, as anyone who studies differential equations, or really as a human in society, being able to interact with data and results like this, understand how they interact with it and how they behave. It's an important skill to have going on into society, and will be for the foreseeable future. So have fun with this. I'm excited for this lab. I know this lab might seem a bit out there, but it's fun to see how this all interacts. And take your time, have some fun with it. It shouldn't take too long once you start playing with these parameters, but have some fun with it and see what it looks like and see what you think this would mean in terms of a real-world scenario where this could come into play.